All right, so let's go ahead and take a look at the next couple of problems. Let's go probably from number 4 to 6. Thanks for taking the time to study. We're going to start off with some posits. Remember, when we say g of f of 14, that means we're going to actually find f of 14 first, and we're going to plug that into g. So I know that some of you would look up here and see the number 4 very rapidly, and I'm totally good with that as long as you're perfect. But I think it's really smart to go ahead and replace the x with that number to show where that number came from. That way, if you made a mistake, you're not going to get totally losing all of your points for that, okay? So we now know that f of 14 is the number 4, so I want to find now g of 4. So g is x plus 1 over x minus 2. Of course, we're going to replace both of those g's with the number 4. And we're looking at 5 over 2. We're good to go. Pretty simple problem. Now, every year people struggle with this one a little bit just because it's like a notation that when they first start, they don't really realize it. But this really means to take f of g of f of 7. And I know that bothers people because, like, why would you use a different notation? Well, different mathematicians at different locations in time came up with different ways of saying this because they didn't know somebody else had a different way. So they kind of invented, and you've seen that in other places. There's different mediums to do the same information. So f of 7 would be to find f, which is x plus 2. And I got the number 3. But since this is 3, I'm going to find g of 3 now. And g of 3 was g of 3 is going to be 4 over 1, which is 4, I guess. And then once we found g of 3 is 4, then we're going to find f of 4. And we finally had everything crash down and was also nice and pretty until this moment, and we got root 6, and we're done. Now, the last one is not really a very difficult one. It's the composite of h of k. Again, this is a different version of saying that same exact piece of information. So I'm going to go find the exterior function h, which is 3x minus 2 over x minus 5. But in each of those places, I'm going to stuff the number k of x, or the equation k of x here and here, which is x plus 1. Now, technically we are correct, but we don't really like to leave things in the technicality. You wouldn't really like it if somebody served you a meal and they said, technically I gave you your food, but I just didn't bother to cook the chicken, right? We want to actually finish it up and make it look right. So if we distribute here and here, it looks like I had 12x plus 1 over 4x minus 4. So that would be the value of h of k of x, which is a nice equation, which leads us to the more significant question about the domain. Now, the domain asks me to find out what values of x I'm allowed to plug in into this function. And the two things that we've said so far this year that we don't want to do is we don't want to divide by 0 and no square roots of negatives. And clearly, dividing by 0 would happen if I made x 1. So my domain is that I do not want to have 1. I don't need to worry about square roots, but I am supposed to look at the inside function k and make sure that there's not some inherent, that's what we call it, an inherent problem from that composite. So if you look back at k itself, k has no restrictions. So it doesn't bring any troubles to the story. So we actually get to ignore k since it didn't bring any restrictions. So the only restrictions came from the composite itself. Okay. Next page is a super easy page. It's just visually thinking about the kind of symmetry that we have. Hopefully you can tell that this graph right here has origin symmetry, that this portion of the graph spun around the origin gives you this portion of the graph right here. In other words, f of negative x is the opposite of f of x. This is an odd function and it has origin symmetry. Similar logic says that this is also odd. It also has that origin symmetry. The spin that exists right here is right here. You can see how that works. If you literally spun your paper 180 degrees, you would not be able to tell the two graphs from each other, okay? They look the same. This guy is even because it has y-axis symmetry. These are perfectly the same, but this one is a little bit trickier. And I purposely did that because what you'll see is if it has origin symmetry and I can spin it, I'm going to grab this little piece right here. And not that this is the most significant piece, but I was hoping it would become clear if I did this. If I grab this around the origin and I spin it 180 degrees, there we are. You can see, and it's a little bit picky, but you can kind of tell that they don't line up perfectly. And see how this is below the axis? That means if I spin it, it should be actually above the axis. And so it's close, but it's not quite there. And the reason it didn't work is because if you look really critically, right there, it actually hit the X, it hit the right below the origin. So if I spin it, it immediately is going to force it to be sitting above the origin. So it cannot have that. So it's not odd. It is not even. We actually say that it has neither form of symmetry. Okay? Now, last one, number 6 for this video. I realized earlier I screwed up, and so I'm redoing this video because I made a silly mistake on one of these. But I hate to have a permanent mistake in a video, so I just started over. So in 6, this is a polynomial. I don't want to divide by 0, but there's. I don't want to take a square root of a negative, but there's no square roots either. This domain is all reals. You could also say that it's everything from negative to positive infinity. That's a valid way of saying that as well. So we're good to go. Anytime you have a polynomial, it doesn't matter if it's x to the 4th, x to the 3rd, x to the 9th, you name it. Any nice set with whole number exponents, it's going to be all reals. But this is called a rational equation. And all of a sudden, we have the possibility that we may have divided by 0. So my domain is that x cannot be 4 and x cannot be -3. Now, what I did do, you'll notice just by force of habit, I factored the top and the bottom because not only do I know now the domain, because that was the question, but I also know that at -3, this guy is a removable discontinuity. There's a problem in the domain, but it's infinitely small. Whereas this one is a non-removable discontinuity. You're going to see a vertical asymptote graph. Okay, so because I did the factoring, now I know where the problems are, but I can also indicate what kind of problems they are. And the last one, this is the one I made a boo-boo on. I actually missed a negative sign because I just wasn't paying enough attention. But I really want to make sure that I don't divide by 0. And I want to make sure that I do not take the square root of a negative. Now, I've kind of tried to make sure I was very clear. Every time you see a square root, I want to see a number. So I know that at -4, I would end up taking the square root of 0, which is actually okay. I know that -2, I would take the square root of 0, which again is okay. I also know that -3, I would actually be dividing by 0, which is not okay. And so now I've created this story that has 1, 2, 3, 4 regions, and those regions are always going to be in blocks. Like if something out here is false, then everybody out there is false, meaning I can't use that place. So if I picked a number out here to the right of -2, and I could use 0 or 10 or 50, it doesn't matter. What I don't want to do is take the square root of a negative, right? So if I tried any number above -2, like 10, I get 14 times 12. That's positive. I can take that square root all day long. This is great. There's nothing wrong. I'm taking the square root of a positive and I'm dividing it by a number, and that number is not 0, because 0 is right here. If I tried -2.5 right here, this part would be positive, but that part would be negative. And a positive times a negative is a negative. And I'd be taking the square root of a negative, which I can't do. That would be bad. I don't want to do that. Now, usually we get yes, no, but I wouldn't really recommend that on a test. You want to really make sure your logic is sound. If I tried -3.5, this still is positive. -3.5 plus 4 is still positive, but -3.5 plus 2 is negative. This is a positive times a negative, which is again negative. I don't want to be here either. Interesting. That broke kind of the cycle. Square roots can be funny that way. And then if we go below -4, like -8, this would be negative, as would this. And the product of a negative and a negative is a positive, and that's okay. So my domain on this problem would be all of the values from -infinity to -4, and then all of those values from -2 to +infinity. And interestingly enough, I didn't even need to mention the number -3 because it was all in this region that everybody was bad anyway. So it really was not a relevant player in the domain. It would definitely affect the way the graph looks, but it won't affect what numbers I can plug in and come up with answers. So I hope that that was helpful. I will see you back in class soon. Thanks for studying. I'll see you later.